Hey guys, Dr. Cadell here, and this is the KSP experiment. So what we're going to study here in this experiment is the equilibrium constant for the dissociation of potassium hydrogen tartrate, which is this compound right here. And what we're going to get out of it is one of the things we're going to find is the value for the KSP at different temperatures, because remember, K depends upon temperature. Knowing that, we're going to be able to use this equation. We're going to plot natural log of KSP versus 1 over the temperature in Kelvin, and this is the equation of a straight line. Y equals mx plus b, where the slope is negative delta H over R, that's the gas constant, and the y-intercept is delta S, the change in entropy, over R. So by plotting natural log of KSP versus 1 over the temperature, this is our x here, we can have the spreadsheet give us the equation of the best fit straight line. The value for the slope will be equal to negative delta H over R. So all we do is take that value for the slope, multiply by negative R, and that gives us our delta H. Likewise, the value for the y-intercept will be delta S over R. So we just take that number, multiply by R, and that'll give us our delta S. Knowing delta H and delta S, we can use this equation to calculate delta G. Delta G is delta H minus T delta S. And now, for the temperature here, we're going to use the temperature for part B, which you'll see in a few minutes. Now, the idea here is that the equilibrium constant depends upon the temperature. So if we go over here, all right guys, so the idea is that as the temperature increases, the value of KSP increases. So what we're going to do is we're going to weigh out some KHT, potassium hydrogen tartrate, and dissolve it in some water, and we're going to have to heat it up to do that. And once we do, we're going to then let it cool down. As it's cooling down, we're going to watch it. We're going to measure the temperature, and we're going to see what temperature we first see a precipitate at. Because when we first see a precipitate, at that point and that point only, we know that the concentration of the KHT, the potassium hydrogen tartrate, is equal to the concentration of both the potassium ion and the tartrate ion. That's right here. Because if we look back over here, we see the expression for the KSP, it's equal to the concentration of potassium times the concentration of the tartrate ion. So if we know the concentration of KHT, we know the concentration of potassium, concentration of tartrate, we can calculate the KSP quite easily. And so that's the basic idea. Why don't we go over and start the experiment? All right, guys, so this is the first part of the KSP experiment, part A. And the basic idea here is we're going to first weigh out some KHT, about 1 gram, into a 250 milliliter Erlenmeyer flask. So put the flask on the balance, tear it out. Take it out and put some KHT in until we get about 1 gram. It doesn't have to be exactly 1 gram. As long as we know the mass to 3 places past the decimal, we should be good. Pretty close. All right. So this is a piece of data. Everybody's going to get a different mass, so you have your own mass there. And we're also going to get ready for run 5. Which is the common ion effect. We're going to weigh out some potassium iodide. I'll tell you why in just a minute. So we put a weigh boat on the balance, tear it out. Take the weigh boat out of the balance. Put some potassium iodide on there. And again, we want about 1 gram. Doesn't have to be exactly. Everybody's going to have a different amount. Oh, that's not even close there. Good enough. All right. So this is another piece of data that we're going to need. Let's set that aside for the moment. So the idea here, guys, is we're going to add some deionized water to the KHT. It's not going to dissolve at room temperature. We're going to add about 25 milliliters using a volumetric, using a burette. We need to know the volume that we add of DI water to 2 places past the decimal so that we can calculate the concentration of KHT in here. So we're going to record the initial volume of the DI water in the burette and add about 25 to that. At about 25 mils, we're going to record the final volume. These are going to be 2 pieces of data everybody's going to need also. Once we add the deionized water, we're going to put a magnetic stir bar in here, put it on the hot plate, and wait for the KHT to dissolve, because as the temperature increases, we'll reach a temperature at which it'll dissolve, and then we're going to take it off, put it on the magnetic stir plate with no heat, stir it, and let it cool down. We're going to record the temperature, or monitor the temperature rather, as it cools down until we first start to see some precipitate. At that point, we're going to record the temperature. So we have about 25 mils. We're going to record our final volume. Put the magnetic stir bar in here, put on hot plate, get it stirring, and now we just have to wait for that to dissolve. We'll know it's all dissolved because we can see it's cloudy. The solution's white and cloudy. When it's dissolved, it'll be all clear. So we're just going to wait a few minutes. All right, guys, so now that the KHT is all dissolved, what we're going to do is take the Erlenmeyer flask off of the hot plate, put it on a magnetic stir. There's no heat here, just a stir. And we're going to let it stir, and we're just going to keep an eye on it. And the first sign of precipitate, which is a white cloudiness, we're going to record the temperature. So to do that, we're going to take the LabQuest and with the temperature probe on it and just set it right in there. The only temperature we care about, guys, is the temperature at which we first see a precipitate. All right, guys, so now that we saw some cloudiness appear, we saw a precipitate, we record that temperature at which we first saw the cloudiness, and we're finished with run 1. Now what we're going to do is we're going to add some more deionized water to this solution. What that does is that changes the concentration of KHT because we're diluting it. And so now that the concentration of KHT is lower, that means that the concentration of potassium ion and tartrate ion will be lower. We expect that we will not see a precipitate until a colder temperature. So what we do is we add about 10 mils. Now we need to know to 2 past the decimal how much deionized water we use. That's why we use this burette. So we're going to record our initial volume, 2 past the decimal, add about 10 milliliters. Doesn't have to be exactly 10 as long as we know the initial and the final volumes were good. So we get down around 10, record our final volume of DI. Now, this is still not dissolved, right? There's some solid, so we have to put it back on the hot plate. Let it dissolve again. Once it dissolves, we do the same thing. We bring it back over here, monitor the temperature at which we first see a sign of precipitate, a white cloudiness. We record that temperature. Repeat that for trial 2. This is trial 2, trial 3, and trial 4. Once we're finished those trials, then we're going to do trial 5. Now for trial 5, we do not add any deionized water between trial 4 and trial 5. What we do is we add our potassium iodide. The idea being that this is a source of potassium ion, K+. And what that will do is that will shift the equilibrium to the left. That's Le Chatelier's principle. And what we expect is that now that we've added some extra potassium ion in there, that the temperature at which we first see a precipitate is going to go back up from trial 4. All right, guys, so this is part B of the KSP experiment. And what we're going to do is we're going to get some saturated KHT. we know it's saturated. Matt has it in this water bath, hot water bath. And if we look in there, we can see, we don't have to look, but when we do, we can see that there's some undissolved KHT. That means that the solution above it is saturated. So we're going to measure out a volume of it, about 10 milliliters. And we're going to add it to a beaker, add some water, and then we're going to titrate it using the same setup with the drop counter and pH probe as we did for the pH titrations lab. The reason we can do it like that is because the tartrate ion, one of the ions in solution there, is a weak monoprotic acid. It's monoprotic, so it reacts in a 1-to-1 mole ratio with sodium hydroxide. What I have up here in my drop counter is standardized sodium hydroxide. You will get the concentration of the sodium hydroxide because that's a piece of data that you need. So we're going to titrate it to the end point, and knowing the volume and the molarity of the sodium hydroxide added at the end point, we know the moles added, which is equal to the moles of tartrate, and that's also equal to the moles of potassium, which means we can just multiply those two, and that gives us our KSP. We do need to know the temperature of the solution, so we're going to measure that. So now, guys, we're going to measure out about 10 milliliters of the saturated KHT. It doesn't have to be exactly 10 mils, but we do need to know to 2 passidecimal what the actual volume is. To do that, we're going to use a graduated pipette to pull up the saturated solution and transfer it into a 10 mil graduated cylinder that has marks every 1/10 of a milliliter. That way we can read it to 2 passidecimal, and then we'll add it to our beaker. So let's do that. Notice I didn't measure it with the pipette. That's not what that's for. That's just to transfer it. This is what we measure the volume with. Okay, as soon as we take the 10 mils of the KHT out of the saturated solution, we have to measure the temperature. So we just take a digital thermometer, pop it in there, give it a minute to equilibrate, record that temperature, and then we're good to go. So I'm going to read this to 2 places passidecimal. Everybody's going to have a different number. You'll have your own numbers for this. So I record this to 2 passidecimal, transfer it to my beaker. Now, chances are there's still some KHT in here, so I'm going to rinse this out with some deionized water and add that to the beaker. Now I'm going to add about 100 mils of DI. It doesn't have to be exact. I have roughly 100 mils in here. The reason for the 100 mils of DI is just so this whole setup works. Put this on my magnetic stir plate. I have a magnetic stir bar in here. Now, I've already set the drop rate on the drop counter, on the syringe rather, to be about 2 drops per second. So I know that's good to go. It's in the gate. I have the pH probe in there. Logger Pro set up. It's recording pH versus volume. And so now what I'm going to do is I'm going to start Logger Pro, start the drop counter, and go. All right, so now I'm going to start Logger Pro. That's going before I start my drop counter. Make sure my stir bar is stirring, and turn on my drop counter, and now we're titrating. So just like in the pH titrations lab, we'll know that we're past the equivalence point once the pH versus volume curve finishes going up more or less vertically and starts flattening out again. And we find the equivalence point the same way we did before. We highlight the vertical region, find where the second derivative is equal to 0, and that's all we have to do. So now we're just waiting for the titration to finish. All right, so now that the titration is finished, we've passed the equivalence point. Stop Logger Pro. And all we have to do is find the equivalence like before, and we're done. All right, so guys, now that we have the volume at the equivalence point, we have the volume of KHT added, and we have the temperature of the solution, we have everything we need from part B, and we're finished. That's all there is to it.